Cool. So, hello. Welcome to the first meeting of content. Last week we did a discrete math review, and hopefully, and I know most of y'all probably didn't watch that, but hopefully you guys are confident enough with math notation now, or some basic concepts, that this will make sense. And if not, I can just feel free to interrupt me at any time, and we can stop and discuss it. Okay, so we'll start having an introduction to discrete pair division, and really what I want to work on today is to look at different things that we want, desirable qualities, and essentially answer the question, what is fairness? So for starters, people want stuff, very simply. I don't think that's a revelation to anyone. But there's not that much of it. And it's pretty much why we have economics as a field in the first place. How do we study the movement of resources within a society? Now, economics, a large part of economics, focuses on this from a social perspective. How do people come to make the decisions that they do regarding the movement of resources? And how does that affect large-scale things, small-scale things? But we focus on it in a little bit more of a specific way as computer scientists. And it happens to be a computationally difficult problem as well, to distribute items among people. Especially in a more complicated setting like this one. So how do we guarantee the truthfulness of our algorithm, where people are not going to lie about their evaluations of things? How do we, so it's incentives basically. And how do we even compute fairness in the first place? So before we get into any of that, let's just look at why this matters. So some applications of this. So there's the Indie Hunger Network in Indiana, which is run by Professor Somas of Purdue, or he works with them actually. It's not his individual thing, but they serve a large amount of people throughout Indiana, working on food distribution. And there's also Food Bank Australia, which is nice. And then there's computing resources, which it's useful for, like memory and CPU time, because they're resources too, and estate divisions. So there's one called Split It, and there's another one I was actually looking at right here, called Adjusted Winnage. Yeah. Okay, so how do we allocate a set of goods to a set of people fairly? And it's not that easy, because I've been talking about fairness this whole time, but it's not clear what that means in the first place. So anyone have any ideas? So anyone who I haven't already told this to?
Yeah. Could one definition of fairness be that both people, so a certain good is valued a certain amount to a certain person, so they receive goods in proportion that the value that that each perceives is equal.
Okay, so that's a notion called equitability, where, I be misunderstanding you, but where I think I have so much, you think you have so much, and so on. Everyone thinks they have a similar amount as the other person. Or everyone thinks they have some amount, but they don't actually worry about what anyone else does.
Kind of. Okay. I don't know, just everybody got not an even portion, but the portion that they needed.
Okay, so that's a notion called equitability. I think, if I'm not misunderstanding you.
Okay.
We can think of a really easy allocation in that context, which is the allocation where no one gets anything. Now, I think I have exactly the same thing as you, and you think, I definitely have the same amount as you, and you definitely have the same amount as, and all the way around this room. And then we'll see that that's actually a valid allocation for several contexts, especially when we talk about charity, which is not today, but a different day. So, okay, that's one good notion of fairness, and it is discussed. We'll get to it eventually. Anyone else? Okay. And if you'd like to give spoilers, or you'd like to give spoilers, then also I'm opening the room to spoilers.
You would explain it better than I would.
That's fair. Okay, so we will. Okay, so just before I say what fairness is, let's just give a setting, so that way we can study this more formally. So we have a set of agents called N, and a set of goods called M, which is going to be really hard to say. I need to really enunciate when I'm saying N and M, so that way it shows up clearly on camera. But okay, so every person has a valuation function, right? Give me like this piece of paper, I have some value over it, but then like you may have some value over it that's different from my valuation. And it takes in some bundle of goods and gives you a real number. So these three goods together gives me a valuation of 7. And then maybe this one by itself gives me a valuation of 2. And for every single person, we'll also say that I value nothing as 0, which makes sense, right? It'll be really hard to do things, or at least a lot weirder to reason about things if you start out with some like value of the things you don't have in a way that you have it. Like, it doesn't really make sense. And we also can partition, and we can also describe an allocation to every single person as a partition of N. Right? So if you imagine it like a line. Someone leave? Right.
Someone tried to come in, but I think they left.
Well, maybe we should let them in. I don't know.
He opened the door. I think he was looking for his class.
Oh.
He saw the math on the screen and was like,
No,
Yeah.
we scared away the other guy too.
Okay, so if you imagine these are the goods, then we can just divide that into N parts, and we have 3 people, right? Or in my diagram, we have 3 people. So this will be what the first person gets, this is what the second person gets, this is what the third person gets. That would just be an allocation, and we just describe it by this vector, x, where x1 is some set of everything that the first person gets. And, okay, normally we can say that the evaluations are additive, which means that if you give me these 3 papers, which I said are 7, and you give me these 2 pens, which are like 2, and then you give me all of it, I'll say it's 7 plus 2 or 9, which is all that means. Oh, wait, I thought I had an extra slide in here. I guess not. Oh wait, I removed it. We can also relax this somewhat, so that way we can say, the more stuff you give me, the better. But it doesn't have to be exactly this amount, which makes it harder to read about.
So, and this may not be something that is addressed early on, but like, is there also, can you write kind of a function that symbolizes this? And because like, if you have one thing, or if you have 2 things, maybe the 2 things together are worth more than they each have separately.
Like shoes.
Yeah, or like for other goods, then and the more you get, it's like diminishing marginal value or something like that, where they aren't worth as much if you have more of them.
You could probably study it all under monotonicity, which is just you're always getting a gain by having some more good. But that would be stricter than monotonicity. That'd be, I guess, kind of making monotonicity a little bit stronger as well. And that'd be interesting to study. but I haven't seen anyone talk about it. But I'll think about it for sure.
Okay.
And I'll let you know next Friday or early if I think of something. And there's also other like relaxations of it, but monotonicity is the big one. Okay, so notions of fairness, the thing I promised I'd actually talk about. So one notion of fairness is that everyone thinks they got at least 1 over n of the good. And it's kind of nice because, at least to compute, because we only need to think about yourself. You only need to think about yourself. I don't actually care what you guys get, as long as I get like what I wanted. And in some settings, this is easier than others. Not in this setting though. This one can be tricky, but in a continuous setting where you're dividing like a cake between people, then it can be like much easier than the other problem. So the value of your allocation is at least 1 over n of the entire bundle. And envy freeness, where every agent believes they receive more than other people. So that means you're truly the best off person. Or you could have like the same valuation as everyone else. I don't think I can get this to stop shaking, so I'll leave it like that. But it's not always possible, right? So if you take one good and 2 people, then someone's always going to be unhappy. Someone's always not going to get something because we can't cut the good in half here. And the same thing is true of proportionality, right? The previous example works fine as well. If you take one good and 2 people, one person definitely doesn't think they got the whole thing. Okay, so envy, freeness, and proportionality are related to each other. If you think about, let's just take for a contradiction, that you have an envy-free allocation, which is not proportional, right? So that means you think you got better than everyone else, all right? And it's additive. So you add up everyone else, but you're also less than 1 over n. So that means less than 1 over n. So that means you add up yours and everyone else's, and you'd never get to the total value of n. Does anyone want me to? I feel like I might have to write that down, actually. Do you guys want me to write that down? You can nod. Okay. Is the entire whiteboard visible on camera?
Like there's the part behind your computer. The computer is not.
Okay,
Like,
so I'm just gonna here.
I doubt I can see.
Wait, further right.
Right.
Yeah. Like, left a little bit. Or yeah, just like block out that whole section.
This here.
No, like above. Go up. And then left.
Left. Oh, okay. You mean this part? Okay, that's fine.
Yeah, no, but more like left.
You were left. No, left. Left.
Like, no, like up. Like, okay, it's fine. Just draw to the left.
Just draw up until.
Yeah.
Yeah,
Okay.
like there.
Okay. I'll just write here. And we'll hope that there's not an issue later. But okay, so we're trying to show that envy-free implies proportionality. These are pretty common acronyms. EF being envy-free, prop being proportional. Okay, so assume X is F, but not. Wait, this is the same issue as last week. If none of you all saw the discrete math thing, the text is way too small. So you know what? I might just roll up this for now. But I'll keep the lights on because if it does. So So, the first question is, so what does this mean? It means that for any person, or for at least one person, the value of their good is greater than or equal to the valuation of, or their valuation of everyone else's pieces. For all I and j. This symbol means for every single thing, right? So for every, you can say for every pair, their valuation, one person's valuation in their mind is better than the other person's bundle. But it's not proportional. That also means that v sub I of x sub I is less than 1 over n, strictly less than, times the valuation of the entire bundle. Because so this is just the definition of proportionality, the opposite of the definition of proportionality. And this is just everything. So that means that, so we know that it's additive, right? So we can say that the sum of all of the is equal to, right, the sum of all of the individual bundles of people is going to be equal to the value of n, which is actually, I should say, the value of the union of all of the so I can do this set because of additivity, where the value of all the union of all of the individual parts of the partition are summed to the value of the entire bundle. But at the same time, we know that, but that contradicts this, right? Because now, if I took the sum of this is bigger than this. So v sub I, so I'm actually going to say, I'm going to wrap around this way, and hopefully it's visible. It looks okay from here.
I think it's too faint.
Like, yeah, you might need like,
A different marker.
yeah.
Oh, much better.
Yeah, I think that's better.
The value of, the value of everyone else's bundles is also less than 1 over n times the value of the entire good, right? Because I know that I think mine is the best, and mine is less than 1 over n. So everyone else's also has to be less than 1 over n. So if you do, and in this summation, you're doing this n times. So n times 1 over n times v sub n, which is equal to v sub n. But we can't do this step. This is the only way you could do it, right? Because this has to be, it has to be less than this. Hopefully it's clear why. Or is it clear why this is less than the value of the entire bundle? Nodding is an option.
Wait, so when you pointed the, like you said, this is less than value bundle, what was this?
The value, the bundle, or this over here.
Yeah, wait, so what were you pointing to? Oh, value.
So we said that for this to make any sense, this has to be equal to this. The sum of each person's value over everyone's bundles has to be the same as the value of the entire as the like entire set of goods. But in this case, if everyone's is less than 1 over n, then it's like you're doing, like, for example, some number that's less than 1 over 2 plus some number that's less than 1 over 2,
Mm-hmm.
and asking, is this equal to 1? No, it's less than. So it's the same argument basically, because this is all we've shown is that no person, in my mind, can have value of more than 1 over n, or even equal to 1 over n, and then summing that all together for n agents. So it's n times 1 over some number, or some number times some number less than 1 over n. This is not like correct notation. I'm using it very informally. N times that's a contradiction, and so that they have to be. Yeah. So I write down again over there. Ready to move on to the next slide. All right, cool. Okay, so we show that NB-free can't work for a discrete setting. So yeah, so we know this can't work for a discrete setting. So we can make a relaxation of this and make the problem a little bit not impossible to solve, and say that each person has to receive more than the other good agent if you took away a good from their bundle. And we don't know if effects allocations can be computed in polynomial time or even at all. So we need to, so that's still an open problem in the field of fair division, and honestly it's probably the biggest open problem in the field. And we'll look at other relaxations throughout the semester, if you all stick around, which y'all should. And so written out more formally, it's saying that the value of every person is bigger than or equal to, or greater than or equal to the value of the other person if you took away a random good from their bundle. And that's the same as saying that the value of a person is greater than or equal to the value of any other person if you took away the smallest item in their bundle. Basically, if you imagine your value of theirs as being like a bar, and then this is your bar. This is and then every good in their bundle is at least this difference. So that way, if you took it away, you'll end up somewhere below your bar. And okay, so even EFX, because it's hard to compute, has been relaxed. And it can be computed efficiently for n equals 2 by just saying one person cuts the bundle as evenly as possible, and the other person chooses their favorite piece. The first person is definitely happy because they cut it as evenly as possible, which means that by taking away a good from the other person, they have to have more. And the second person is definitely happy because they choose their favorite piece. They are NB free anyways, so it is convenient there. And we also have an algorithm to compute an EFX allocation in pseudo-polynomial time for 3 people, but it is complicated. And we'll talk about it maybe. I don't even know if we'll talk about it. It depends on how far we get and how fast we can move through this. Okay, so one relaxation that we have in VFX is realized valuations, where every single person shares the same valuation function. we all think about goods the same way, and maybe something like money. You're trying to divide like units of money, which are weird. And EFX exists, and there's a polynomial time algorithm, which I'll explain the meeting after next. And there's also EF1, which is saying that if you look at this line and compare it to this line, you'll notice they're almost exactly the same. There's two changes. The first one is over here, where instead of for all, it's a there exists. So you could take away some good and from the other person's bundle, and that would fix the issue. And the other change is it's the same thing as saying that you take away the biggest item in their set, meaning that you're not just checking for every good that it goes below this line. You just need to find a single good, the most valuable good, the other person's, which brings it down below this line. Another relaxation is alpha EFX, which is where you have like some multiplicative amount better than the other person. This might be wrong. This is incorrect. It should be for all over here. Not there exists, but I think. But is that clear so far? Realized valuations, EF1 and alpha EFX. EF1 is the one we'll see a lot of to start with, and then we're going to move away from it very quickly. Any questions? Okay, and we're on break time anyways, so we can pause the recording. Okay, ready to go. So let's talk about Max-Seeman fair share, which is a tongue twister if I ever heard of it. So there's a lot of notation, but let me make it kind of understandable. So let's say that you don't know which allocation you're going to get. You're just going to be assigned a allocation. And you want to make sure that in the worst case, you're as best off as possible. There are many allocations like that, right? You could, but if you like sort them, they're all the same. So they're all, so basically you're taking the worst person, or the worst off person, in the entire bundle, and making sure that their valuation is as big as possible. And that's all that Max-Seeman fair share means. Really can't say.
You misspelled or you misworded it down there.
Yeah. Wait, no, actually, the top one is wrong. It's Max-Seeman share fair, which is worse for some reason.
Why?
Because the Max-Seeman share is like the concept describing the vector, and you're just saying it's fair with respect to that.
Why not fair maximum share then?
Wait, say that again?
Why not fair maximum share?
Because it's like EFX fairness, proportionality fairness, like a notion of fairness, which describes, or which is described by this vector.
Maximum share fairness.
You're better at saying it than I am. I'm just going to call it MMS, because I can say that. And, okay, so it doesn't always exist. There's a slightly stricter or stronger version of it called GMMS, which we will study at some point as well. And that's saying that it's for every group of a certain size, it is maximum share fair. So for example, for groups of two, it should be maximum share fair for every single pair of two. And so, does that sound familiar? So basically, it has to be as even as possible for every single pair of people in each of their minds. Does that sound familiar? Is that something similar to something we've talked? Is that similar to something we've talked about already? Keeping in mind there's a limited number of things that we've talked about so far. So It's gotta be something. So we're taking groups of 2. That number is important as well. So what are our options? Is it E of 1, E of x, or proportionality, or yeah. Which one between those 3 things is the most similar?
Proportionality?
It is not proportionality. So it's actually E of x. Because if they're as close, I guess the reason it's weird to reason about, and this kind of trend continues with the same pattern, at least to me it seems that way, where you have, if they're as even as possible, then that means if you took away a good from any person, then that wouldn't work, right? That wouldn't be even, but that's okay in E of x. E of x is as even as possible between all pairs of people. Because you have the first person and the second person, and they're as close as possible, and if you took away any one good, then it wouldn't be like as close. So MMS is, or GMMS, group MMS, for 2 people, for groups of 2, is the same as computed. If you can compute that, you've computed an E of x allocation trivially because they're the same allocation. And then you can also relax it by multiplying it by a constant between 0 and 1. Pareto optimality, you don't usually see it by itself, but it's basically saying the allocation where no one is not going to protest. Basically, an allocation is Pareto dominated by another if every single person has at least as much value of their bundle than the other one, and one inequality is strict. So meaning one person is definitely better off, and everyone else is at least as well off as in the second one. So that's like an ordering of vectors, right? A partial ordering of the vectors. And the maximal vectors are all Pareto optimal. And finally, M and L, which is where we're going to stop, unless you have questions. And we're trying to maximize the geometric mean of values. We don't actually care about the fact that it's the geometric mean, so we can think about it as maximizing the product of utilities for agents with positive value. This over here is the utility of agent I. So it's maximizing the product of those. And a maximum Nash welfare allocation will imply E of 1 and Pareto optimality. So you guys wanted an exercise for the readers, so let's do an exercise for the readers. And I also have the answer up here, so if you want to, yeah.
Can you go back to the definition of E of 1?
E of 1, yeah. Not 1.
Wait, that's E for X. Oh, there's E. Okay.
In my mind, it makes more sense to look at the second one, or the second part of it than the first part. Actually, don't even worry about E of 1. Worry about Pareto optimality. Yeah, E of 1 is more complicated. I don't know if I want to explain here. Because it's a lot of inequality and manipulation, basically. And I feel like that gets hard to follow, especially in a YouTube lecture. Especially an optional YouTube lecture. I don't want to scare you all away or after one meeting.
Wait, could you go back to the definition of preto-optimal?
Preto-optimal, yes. I feel like looking at the bottom two will give you a better sense of the answer. Here they do it by contradiction. But you can, and contradiction is easy sometimes because you can just say like, or they use contradiction for stuff that feels obvious if you know the, or if you understand the setting really well. Because then you're kind of just like, yeah, it's obvious, it couldn't be any other way. And then you do it by contradiction, which is like formal, but sometimes it can get hard to follow. But in this case, it's short enough anyways.
Okay.
You got the answer?
No, I was just finally understanding this.
Oh, okay. Yeah.
Okay, could you go back forwards to MW?
Sure, write down the definition over here.
On the board, yeah, forward.
Yeah, so write down preto-optimal and then MNW or vice versa. Which do you prefer? Hand raised for keeping preto-optimal on the board and MNW on the screen.
It's easier to write MNW.
Okay, we'll do that then. So actually next week we'll be introducing a different setting. But it should be very familiar. A lot of things will carry. I started in learning about the continuous setting and realized I like the discrete setting more because it feels close to home as a CS major. But you know, this is definitely showing up on camera, right?
Yeah. One note, or one question. You actually can see I'm writing. And you can see where I'm writing. Yeah.
And finally, this one may not show up on the camera.
Let's say why it has to be TV evaluation?
Positive.
Yeah, positive.
Positive, okay, yeah.
Mm.
Oh, I thought that was a T, okay.
So 2 problems. I'm gonna say, and then I'm also going to say, right, the problem that we're actually trying to solve, which is
So we're proving that PO is the best way to maximize that.
Proving that
no,
that
we're-
allocation is BO.
Oh, okay.
Yeah. Don't think too much about notation. Focus more on what it means.
I guess it makes sense that it's PO because if
Build a contradiction.
Well, I'm doing without a contradiction, I think, maybe, because if, well, okay, because if there was, okay, I guess the contradiction is that if there was an allocation B where that is true, then it's no longer maximizing the product development because the product would be greater if the individual values were greater.
Yep, exactly.
And it also has to be positive because if it's negative, then the inequality is all thrown everywhere.
Yeah. So
Ridiculous
now,
product.
give an example. You can come up with a really easy example, which,
Does a negative valuation just mean that they don't like it?
okay, so in the first slide, yeah, so negative, that would basically be what negative means. It's called Chor division, and it is an open problem. And in fact, EF1 for Chor division is still an open question, so it's harder to solve.
Because it has negatives in it.
Yeah.
I feel like a simple question, because you not just like add just whatever like the biggest negative value is. Let's say it's like the valuation in vision negative. Can you not just like add 10 to everybody's individual valuation or something just to like force it to be 0 or positive, or is that break something else?
So you're kind of playing like number games with evaluations. I don't know. I don't think that would work because the issue isn't necessarily that like you choose a 0 point. Like even here, you can choose 0. You can choose whatever number you want actually, but you still want to be like better off than everyone else. That's kind of what EFX is about. And if everyone starts at the same point, then it doesn't really matter what you start off at. It can be like 2 billion, and then it's still kind of okay. But I think it's more to do with the fact that it's not clear which good you should give to any person at any given point when you're distributing the goods in any algorithm. It's not clear who you should give any good to or like immediately. But if you have any thoughts, the server is a good place to keep them because I also put a fair amount of ramblings in the. If any of you guys have seen a fair amount of like, what if something, and then no response. But yeah.
And I guess the reason why you can't add a flat thing is like it's inherently like bad. Like adding positive values to make the value positive changes the meaning of your valuation. Like your valuation was originally negative. Like I absolutely detest this thing. And I think it means something different when like if you say like okay it's kind of better, but like everyone else is getting way better ones, so like it's still like so much worse than me, but I don't know, I feel like it means something different when you add something to it, and it also would change the product things as well, right? Because if like let's say your valuation of like doing the laundry is like -1,000 and everything else is like valued at like 2, right?
Scale it up to like 0, 1,002, that throws everything off.
Yeah, that throws the products also off. So
Yeah.
I gotta go, but
Bye.
An MNW an MNW one can be computed efficiently. Usually people care more about the polynomial computability than like a specific like polynomial. You know what complexity theory is. Do you guys know about like asymptotic complexity?
I didn't get that last part. But
Asymptotic complexity.
there you go.
Like yeah, big O.
gotcha. Yeah.
Do you know big O?
Oh, big O, like notation? Yeah.
I didn't talk about it last week.
No, I think they did talk about it at Codeburners though.
They have more long. I didn't know that.
I only went to one.
I went to today's. Apparently Chituri is going to Student Union after.
Why? Yeah.
Like he's bringing the bag of snacks. So yeah. Like he just brings a bag of snacks and like takes like